Okay, so good afternoon, everyone. Welcome to this seminar that is organized by UNSW, which is also part of the Statistics Across Campuses initiative. So today we have Professor Martin Hazelton. Martin is based at the University of Otago, where he's head of statistics and professor. Prior to that, he spent a few years at the Massey University, also in New Zealand, and before he was in Australia at the University of Western Australia. So some of the research interests for Martin are statistics of linear inverse problems, smoothing methods, spatial statistics, etc. And today, Martin is going to speak about dynamic fiber sampler for linear inverse problems. So Martin, the floor, or the virtual floor is yours, and we will try and keep the questions for the end. Thank you.
Okay, Boris, thank you very much for the introduction. I've actually been suffering this week from despite the fact we're not COVID ridden here in New Zealand. I've been suffering from a bit of a head cold, so if I get hoarse in the middle, I do apologise. But at least because it's a virtual session, I can't cough all over you. Anyway, like Boris said, this talks about dynamic fibre samplers for linear inverse problems. So I guess I'll start off talking about inverse problems. So an inverse problem occurs when we're interested in some symbol, we call that X all the way through, of interest. We don't observe it directly. We might observe a corrupted version of it or some kind of summarized version of it. And problems of this kind are ubiquitous in science and technology. A couple of classic ones appear on the slide, image deblurring and computed tomography. So obviously in image deblurring, you'd like to know about, if you like, the X describing the true image, but you get a corrupted version. In computed tomography, you want to know about a three-dimensional body. You only see summaries in terms of two-dimensional slices. So the two examples of inverse problems I've just discussed, they're both in the continuum. I'm particularly interested in linear inverse problems for count data. So if you don't remember anything else from this talk, try to remember equation 1, y equals ax. Okay, that's an important equation in the talk. So x, as I said, is our variable of interest. But what I observe is a variable y. So a little bit more notation. Y is related to x through a matrix A, that's called the configuration matrix. And that's going to be a binary matrix for all the problems that I'm looking at. And that matrix has got dimension n by r. So what I'm thinking of here is that the dimension of the observed count vector is n, and the dimension of the vector of interest x is r. And typically, r, dimension of the vector of interest, is going to be a lot larger n, the vector of counts to observe. So that linear system in equation 1 is going to be underdetermined, typically heavily so. Our aim is going to be to perform inference for x and or a parameter vector theta describing the underlying probability distribution for x. And typically, we're going to hope to have some prior information or auxiliary data to regularize the problem. So some examples. I mean, there are loads of examples of inverse problems for count data. The one that really got me interested in the area was network tomography. So in network tomography, we are interested in a vector x of path traffic flows. So you've got a network, and you've got traffic flowing through the network. As I said, we're interested in the path flows through that network, or perhaps more usually, the mean path flows. So my theta is here, a vector of mean path flows. But I don't observe those. All I observe are some traffic counts vectored at various network locations. That's going to be my vector y. And so trying to
Sorry, sir, I'm unable to hear anything. I'm unable to see anything. You can't recollect. Try to rejoin the session. Oh.
The path that starts at node 1, goes through link 1, goes through link 2, and is destined for 3. So the first path connects node 1 to node 3. The second path, second column, A, uses links 3 and 1, and so that's the path that starts at node 3 and ends up at node 2, etc. You take a look at, for example, the very last path here, the sixth path, it just uses link 3, so that's for the path which is about travel that originates at 3 and is destined for node 1. And so I say here's a classic topography problem where the dimensionality of the observed counter vector y is rather less than the dimensionality of the vector of interest x, that vector of traffic path flows. Another classic example that can be thought of as a linear inverse problem is resampling contingency tables conditional upon marginal totals or similar statistics. So there's a variety of applications of resampling entries of a contingency table. It can be used in exact inference. It can be used when confidentializing cross tabulations of official statistics, etc. But actually, I find it one of the less interesting linear inverse problems. There's other ways, typically, of analyzing contingency tables, but because it's a very familiar setting for statisticians, it's actually the setting I'm going to use as ongoing examples through the talk. So I say it's not that I think this is a particularly important example of a linear inverse problem. It is an easily recognizable one. So anyway, so what we've got here, we've got a 2x3 table. So the row totals here are y1 and y2, the column totals y3, y4, y5, and the individual cell entries x1 through x6. And the relationship between the y's and the x's again follows my linear system, y equals ax. One of the things to note about this linear system here is, in fact, it's not a full rank. So the matrix A is not a full rank. And the reason is that once you have, you know y1 and y2, you know the total of observations in the table, total sample size n. And so if you then know y3 and y4, you can determine y5 automatically. So y5 is redundant, and in fact, so that final row of the matrix A is redundant. So we're just going to delete that. So I'm going to assume throughout that we've deleted any redundancy in A, and so that A is a full rank. Other applications in capture studies in ecology, we will be interested. So in capture recapture studies, you go out to some location, you record animals that you cite. You go back the next day and you do it again, and the next day you do it again. So you get a number of observational periods and you record things that you cite. And what you're interested in is the pattern of sightings. So for example, you might be interested in the count of animals that you saw on day 1 and day 3, but not day 2. And you could let, for example, Y101 denote that count. That's a count of animals that you observed, say, in both periods 1 and 3, but not in period 2. Now, in principle, from such data, you can do things like estimate population sizes. There's an issue here, which is that the count that you think you have of animals observed just in periods 1 and 3 might be wrong, because you might have misidentified some of those animals. You know, a particular animal that you thought you saw in periods 1 and 3 only, in fact, you made a mistake. The animal that you saw in period 3 was actually a different animal. It just looks rather like the first animal. So, to account for these possible misidentifications, the vector of interest is in fact x, which takes account of the misidentifications. Y, if you like, is a corrupted version of that. Again, the relationship between y and x can be described as a linear system, y equals ax. Another example is in biosecurity surveillance. So what we've got here is you've got, for example, mail items that are coming through, and you're interested in catching any of them which are biosecurity risks. You stratify them to start with based upon their expected risk, and depending upon the strata, you send them through a set of compliance tests, and that will vary for each item, say, dependent upon this prior estimate of expected risk. And so what you're going to end up with is a cross-classification of the outcome of each compliance check at each stage. That's what we'd like to know about, but we only observe a summary again of those data, and so again it's an example of a linear inverse problem. So we're interested in x. That's what we would like to have observed, but we observe only y. So our inference for x given y is going to be obviously controlled by the conditional distribution f of x given y, and have suppressed dependence upon the parameter just for notational convenience. What can we say about this conditional? Well, we can apply Bayes' theorem. So f of x given y, apply Bayes' theorem, f of x, f of y given x over f of y. F of y given x, well, y is deterministic in x. So the distribution of y given x just collapses to the indicator of the event y equals ax. In other words, if y is compatible with x, y equals ax, then you get a 1, otherwise you get a 0. F of x is the marginal for x, for which we have a mass probability model, and f of y here is the marginal for y, and that's given just by the sum of f of x values. Notice this sum has is taken over script f of y. The script f of y is something called the y fibre. That's the solution set for my linear system. So because I'm dealing with count data, that's the solutions x, the system y equals ax, which are non-negative integer vectors. So that's called the y fibre. It's going to be an important idea throughout the talk. So let's take a look at what y fibres look like. Let's go back to our 2 by 3 contingency table, and suppose that we've got row counts 3 and 5, column counts 2, 4, 2. The observed vector y here is 3, 5, 2, 4. Notice that the final y5, I've ignored that, it's redundant, you'll remember. So what can we say about the y fibre here? So the y fibre is the set of entries to this contingency table, x1 through x6, that are consistent with those row and column totals. Now, since I've got 4 constraints, 4 entries in y, these are linearly independent, and 6 entries, it follows that I have 2 degrees of freedom here, and so the set of feasible counts can be specified just by the values of, say, x1 and x2. That's pretty clear. You know, once I know x1 and x2, the value of x3 is automatically determined by the row constraint, and then the values of x4, x5, x6 are then immediately determined by the column constraints. So as I said, the entire y fibre here can be specified just in terms of x1 and x2. What do I know about them? Well, another x1 must lie between 0 and 2 because of its column constraint. Another x2 must lie between 0 and 4 because of its column constraint. And I know that x1 plus x2 must be less than 3 because, or less than or equal to 3 because of the row constraint. But x3 can itself be no bigger than 2. So in order to get a row total of 3 on the first row, x1 plus x2 must be bigger than 1, greater or equal to 1. So those inequalities I've just indicated are what the y's are telling us about the x's. So let's have a look at what that looks like. As the first constraint, x lies between 0 and 2. Second constraint, x2 lies between 0 and 4. Third constraint, x1 plus x2 lies between 1 and 3. That's actually the third and fourth constraints. So like you might have done when you did linear programming at high school or early at university, you get this feasible set. So that's what the grey region is. It's a feasible set if you're working in the continuum. But of course, I'm just dealing with counts. So my feasible solution set is just the integer valued points within that grey area, which is noted by those black dots. So those black dots are the elements of the Y fibre in this particular example. In general, that grey polygonal shape you just looked at is an example of something called a convex polytope. That's what happens when you look at the solutions to the non-negative solutions to linear systems y equals ax in the continuum. Now, as I said, I'm only interested in the lattice points, the integer lattice points on that in that polygon. So I'm interested in a fibre which takes the form of a Z polytope. So the Z polytope is simply the lattice points, the integer lattice points within convex polytope, and so my Y fibre is geometrically speaking a Z polytope. And thinking about the geometry here turns out to be very useful when we come to do sampling. It's going to allow us to do efficient sampling by thinking about the geometry of the underlying polytope. Now, assuming that the matrix A is a full rank, as I said, we just delete redundant rows as necessary, then the Y fibre is an R minus n dimensional object. So R is the dimension of X and n is the dimension of Y. So it's an R minus n dimensional object embedded in R dimensional space. And that means I've got flexibility in terms of the representation. So thinking about that contingency table example we just dealt with, I told you before that we could express the points on the Y fibre in terms of the entries x1 and x2 of the contingency table. And that's what I've done on the left-hand plot in this slide. But equally well, I could describe the entries of the contingency table, in other words, elements of the Y fibre, in terms of just x5 and x6. So the grey shapes are just two different projections of my polytope, just on, say, different representations. And just as a sort of a concrete example, the table with entries 2, 0, 1, 0, 4, 1, if we look at it in terms of x1 and x2, then it's just specified by x1 is 2 and x2 is 0, so that's specified by the gold dot on the left-hand plot. If we described it in terms of x5 and x6, then it's described here by the coordinates 4 and 1. Same table, just described by different entries of x. Here's an example from network tomography. So what I've done here, to make life a little bit nicer, if you remember originally, my network tomography example that I gave you had 6 paths and 3 link counts, which meant that the polytopes would be a dimension 3. And that's hard to draw on the slide, okay? So what I've done is I've just deleted the final path. So there was an extra path available, but I deleted that, so now I'm only allowing 5 paths of travel. And that now means that my matrix A corresponds to a system with 5 paths and 3 link counts, And that's nice because it means that my polytope now is of dimension 2, and so I can draw pictures easily. And again, I can do the same kind of game as for the contingency table. I can display the polytope in the continuum, the grey and shaded areas, and the lattice points within it, so the points in my fibre, the black dots. I could display them, for example, with respect to coordinates x2 and x5, or x4 and x5, or x1 and x2. Again, just different projections of the same polytope. But so curious differences in appearance. We'll come back to that in a little while. So, a lot of the time when you're dealing with linear inverse problems, you're principally going to be interested in doing doing inference for the parameter theta underlying that variable of interest x. And so you'd probably want to know what the likelihood is. So the likelihood for theta, which is of course just the probability of the observed data given theta. Well, we saw what this marginal for y was previously. It's the sum over all elements of my y fibre. In other words, over all x vectors consistent with the equation y equals ax of the probability mass function of x. So, whether I want to just learn about the x's on their own and forget about the thetas, in which case I'm sampling from f of x given y, and I need to know the normalizing constant fy, or I want to do likelihood-based inference for theta, in both cases I need to evaluate a sum over all entries of the y fibre. And that's a problem because typically these fibres are too large to enumerate. So again, let's play a game. Here's a contingency table. Question: how many alternative tables are there on the same fibre? In other words, how many alternative tables are there with the same row and column totals? Give a moment to try and guess. And for some reason, I have lost the next slide. The answer is anyway, a lot. It's, I think from memory, it's something like 10 to the 18. So many apologies for that. I don't know what happened to that slide. Anyway, so in general, if you evaluating a sum with 10 to the 18 entries is clearly infeasible. So for nearly any practical linear inverse problem that you're going to come across, the y fibre is going to be far too large, have far too many elements to evaluate. So what can you do? Well, typically the statisticians face this kind of situation, you would just sample from a set that's too large to enumerate. And in fact, that be implemented using either sort of common techniques like the stochastic EM algorithm or MCMC if you're doing Bayesian inference. So for a stochastic EM algorithm, you're going to fix the parameter theta, and you're going to resample x's as you try to maximize the likelihood. For MCMC within a Bayesian setting, you're going to iterate between drawing samples of theta conditional upon x, which is usually very straightforward. As I say, typically the probability model for x is going to be nice, so you might even have able to do this by Gibbs. But we need to iterate that by sampling x given y. And in both cases, it's the sampling x given y that's the challenging step. So to summarize what we've got a linear inverse problem. If we want to do likelihood-based inference, or if we just want to resample the x's, we've got the problem that the set of possible x's, the y fibre that match or are consistent with my observed data, is far too large to enumerate, so I need to do some sampling. Okay, I'm going to have to stop sharing my screen for a second because I'm losing my slides and I've got no idea why.
Martin, do they display fine on your computer?
No, they've just stopped displaying on my computer as well, which is odd. So, okay, many apologies. I think what happened is that the slides are on a network drive and the network drive just cut out. So unfortunately, it's only I lost like half of them. Let's try again. Okay, we seem to be back working again. So there, by the way, was the answer to that, how many contingency tables were consistent with those totals. And now let's press on. So as I said, what we want to do is we want to sample from our Y fibre, which if you remember has the form of this Z polytope. So to sample from a distribution f of x given y, which is supported on that polytope. And we're going to use a random walk metropolis Hastings sampler. This is what everybody uses for these kind of problems. For example, rejection sampling is hopelessly inefficient. So standard kind of setup, we've got a current state x. We're going to generate a candidate x dagger by drawing a move z from some set S of moves, drawing a step size b from the integers, and then creating x dagger is x plus b, the step size, times z, the move. And we will then accept or reject that in the usual way. Now, if this algorithm is going to work at all well, then we're going to need the x dagger, the candidate that we draw, to be on the Y fibre. In other words, to be a consistent data point, consistent with the observed Ys. And that's the tricky thing. So to keep things simple, let's for now just focus on moves of length 1. So suppose we're just trying to get a step in my random walk metropolis Hastings of length 1. Now, if the move z is to have any chance of being accepted, I require two things. Firstly, I require that my linear system still applies for the proposed value. So in other words, x dagger must still satisfy ax dagger equals y. Now, because x dagger here is just x plus z, remember, just taking a unit step, it follows that az is 0. In other words, z, the move, must be in the kernel of A, of course, because I'm dealing with the integers within the integer kernel of A. But the other thing I require, because I'm dealing with counts, is that my x dagger must have non-negative entries. In other words, x plus z, all the entries must be non-zero. So in this requirement 2, inequality is to be interpreted element-wise. So how might we go about finding some moves with those properties? Well, let's deal with property 1 first. A lattice basis is by definition a basis for the kernel of A, the integer kernel of A. How could we get a lattice basis? Well, here's a nice simple way. Partition the matrix A into A1 and A2, where A1 is an n by n invertible matrix. Remember, A is a full rank, so we can certainly do that. and partition the x's likewise into x1, x2. And now define the matrix U as follows. We've got a block at the top, minus A1 inverse A2. At the bottom, we've got the identity matrix of dimension R minus n. Then it's trivial to show that AU is 0. So in other words, the columns of that matrix U that we've just created form a lattice basis. They'll move us around the integer kernel of A. What's kind of interesting about this lattice basis that we've just constructed is because we've got this identity matrix at the bottom, what's actually happening is that the moves in this lattice basis correspond to the coordinate directions in the polytope projected onto the column space of A2. In other words, in terms of the entries of vector x2 in this partition of x. Here's a little example with our contingency table. You can, doing that, what I've just said, you could create a couple of lattice basis vectors here, U1 and U2. U1 looks like 1, minus 1, 0, minus 1, 1, 0. And the effect this has on the table is as follows. It increments the top left entry by 1, decreases the center top entry by 1, decreases the bottom left entry by 1, increments the middle bottom entry by 1, and just affects the right hand entries. And similarly, we've got a vector U2. And so let's suppose that our current table is 2, 0, 1, 0, 4, 1, expressed as a vector, which looks like the contingency table down here. Then, if we move the direction minus U1, x minus U1 is 1, 1, 1, 1, 3, 1. So we've found a new contingency table here, which is consistent with the same row and column margins. So it's on the same fibre. So what's happening, let's look at pictures here. So the red dot with x over it, it corresponds to the original contingency table. That's this guy here, 2, 0, 1, 0, 4, 1. And I'm using a projection in terms of x5 and x6. And if I travel minus U1, it means I just move to this lattice point in the center here. And it should be pretty obvious that by taking moves in the coordinate directions, x5 and x6, I can walk around that lattice, that Z polytope fine. So it's subtitled as Walking on Sunshine. You notice there's one or two musical references to the talk. I would give out a chocolate fish if I was there for anybody who spots them all. So anyway, here it's fine. You can walk around the table fine using that lattice basis. Here's another contingency table, still a 2 by 3 contingency table. Now the row and column constraints, totals, are 1, 1, 0, 1, 1. And the Y fibre has only 2 entries. There's only 2 tables that are consistent with those marginal totals. And in terms of the projection, in terms of x5 and x6, you notice you cannot travel between the 2 black dots by moving in the coordinate direction without leaving the polytope. That's bad news. It means that, for example, if I try to sample using those lattice basis vectors U1 and U2 as my possible moves, I couldn't, I'll start generating vectors that are not on my Y fibre. I can't get to the other points in the Y fibre by using those moves. That's clearly a problem. Road to nowhere. Here's another picture that relates to that network tomography example that I introduced earlier. What's quite cute here is this is the projection for that example in coordinates x4 and x5. And you notice that the black dots kind of form a Swiss cheese. There's some holes where you might expect to see black dots. No mistake, there really aren't any black dots there. So if we move around in the coordinate directions, in other words, if we've constructed a lattice basis that corresponds to coordinate moves for x4 and x5, I can walk around the y fibre, the z polytope, but there's a whole lot of points I can't reach. You notice that I can't change the parity of x4 and x5. If I start at 0, I can only get to x4 is 2 or 4. I can't get to x what values 1 or 3. So what have we seen? We've seen that whilst a lattice basis will allow you to walk around the z kernel of A, the integer kernel of A, it will not allow you to walk around the entire y fibre. What happens is you end up needing to leave the fibre if you wanted to get to some of the other points. And that's bad news. Now, if you can't reach some of the points in your fibre, then it means that your Markov chain that you're running is not going to be connected. And so you're certainly not going to have an irreducible random walk. And so you're not going to converge to the required posterior distribution. So what we need to do is we need to have a set of moves in order to generate new candidates that mean that I can connect any 2 points on the y fibre. And ensuring this connectedness is rather difficult. Indeed, just recognizing that this connectedness might be a problem is not something that many researchers realized until just over 20 years ago. So what do we need? Well, what we need is a Markov basis or a Markov subbasis. So a Markov subbasis is a set of moves, here I've called them Z1 through ZL, such that you can travel between any 2 points, called XA and XB, on the Y fibre without ever leaving the Y fibre. In other words, there are a set of moves that allow me to connect my Y fibre. Now, a set of moves is a Markov subbasis if they connect a fibre for a given Y. A set of moves is a full Markov basis if they connect any fibre. So for any, so for a given matrix A, for any observed vector Y, they will connect the fibre. Of course, in practice, the Markov subbasis is typically sufficient, but actually there's no good way of finding those. At least there are ways of finding full Markov bases, and they're generally useful. So as I said, there are ways of finding Markov bases. And I said, a moment ago that the issues involved in fibre sampling, the problems that you see, you might not have connectivity for these kind of linear inverse problems, that was really sort of brought to many statisticians' attention by the seminal paper of Diaconis and Sternfels in 1998. And what they showed was that you can find Markov bases using techniques from algebraic statistics. So the idea is that you represent a point x in your fibre as a monomial, as a polynomial with an integer coefficient. So t to the x in vector form looks like t1 to the x1, t2 to the x2, blah, 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 through tr to the xr, where the t's are just indeterminates. It might sound like a strange thing to do, but the reason why this is useful is that moves can then be represented by monomial differences. And so walks through the fibre can then be thought about in terms of long divisions of polynomials. And there's the entirety of polynomial ring theory that tells you about what you can and can't do there. So certainly we've got some huge mathematical machinery that can apply to the problem. So it turns out you can actually calculate Markov bases by using the Grobner bases for the toric ideals of monomial differences. And this is all implemented in software called 42. The answer to everything, of course. So that seems good. We set ourselves the problem of sampling from this fibre. We saw that lattice bases didn't do it, but Markov bases will give us connectivity. But there's two problems. Firstly, a full Markov basis is very computationally infeasible. That mathematical machinery from polynomial ring theory tells you how to do it. This is called Buchberger's algorithm, which will implement it for you. Actually, it doesn't scale at all well. As soon as you get to realistic size problems, the whole thing falls over. Secondly, samplers using full Markov bases can mix extremely poorly. The problem is twofold. Firstly, Markov bases may contain useless moves, and secondly, a full Markov basis takes no account of the geometry of the underlying polytope. So, if you are sampling from a posterior distribution, some things that you may be aware of and using MCMC, and your posterior distribution is long and thin, then statisticians are aware that you try to get a proposal distribution that somehow reflects that long thinness. Same thing is going to apply here. So as I said, Markov bases can be far larger than you need. As an example, if you wanted to resample an I by j contingency table, the full Markov basis has order I squared j squared entries. So for a 20 by 20 table, it has about 35,000 entries. But in fact, you can find an adequate Markov subbasis. So for a given y, a given set of marginal constraints, typically with only 361 elements. So there's a lot of unnecessary entries in that full Markov basis. It's a network tomography problem. The network corresponds to an internet connections over the US. And there's only 12 nodes in this network. It's a very simple network. 132 paths, 42 links. So if we try to do network tomography for what's really a very small network, it took the software 42, which is state of the art, over 9 hours to find a Markov basis with almost 11,000 entries. But clearly, for lots of realistic network tomography problems, they're just not going to fly using Markov bases. So the problems with calculating full Markov bases ab initio led Adrian Dobra to introduce something called a dynamic Markov basis. So his idea is, you are doing your random walk, you find yourself at some particular location X, and there you create a suitable set of local moves in some simple way. And so long as the union of all the sets of local moves forms a Markov basis, one or two technicalities, but nothing too hard, the resulting walk should be connected. Now, Dobra did a lot of this. He did his work on focusing entirely on contingency tables, and he also ignored the geometry of the polytopes. So whilst this methodology is nice, I find it to be very slow mixing in some cases. So our idea is to create a geometrically aware version of Dobra's dynamic Markov bases that can be used on any kind of linear inverse problem. And the way that we're going to do it is we're going to use lattice bases. So remember I said earlier that a lattice basis isn't going to connect your fibre. However, also remember that I said that there are many alternative representations of your polytope. In other words, when you partition the matrix A to construct a lattice basis, the choice of what goes in A1 and A2 typically be huge variety of choices. So huge numbers of different lattice bases that I can create corresponding to different representations of the polytope. So let's, a little bit more notation. Let's denote by pi a partition of the numbers 1 to r. Remember, r is the dimensionality of x. And let's partition that into two sets, k1 and k2. K1 is of size n, and K2 is of size r minus n. And K1 is going to be the set of columns of A that are going to go into A1, and K2, the set of columns that are going to go into A2. I'm going to denote, therefore, by A pi, the submatrix of A formed by the columns indexed by Ki. And I'm going to let capital pi be the set of all partitions so that A1 pi, that first partition, so that first partition under that permutation I is invertible. And so for any partition within capital Pi, I can construct a lattice basis corresponding to the columns of this U matrix U pi. And so that corresponds to coordinate moves with respect to the columns of A2 pi. So again, let's return to our ongoing example of the lattice basis, of the 2 by 3 contingency table. So here is, remember, the representation in terms of coordinates x1 and x2. And because the lattice basis looks like moves in the coordinate direction, lattice basis is moves looking like these red arrows. The middle picture is the representation in terms of x5 and x6. And so the lattice basis in terms of those coordinates looks like the blue moves. Again, coordinate directions. I can ask the question, what do those blue moves look like in terms of the representation x1 and x2? So we're going to move the blue moves into this left-hand representation. That's what I've got on the right-hand side. The representation is in terms of x1 and x2, but moves in the coordinate direction for the lattice basis for x5 and x6. Now, the blue arrows, notice that one of them is diagonal, so I'm no longer moving in directions. So what this is telling me is that if I take different lattice bases, then for any given representation, they're going to give me moves that aren't just in the coordinate directions, they're going to be in diagonal directions as well. Those extra orientations are going to be critical. Here's some nice theory. All you need is lattice bases. So recall that I've got some lattice bases corresponding to each partition of A. And I'm going to focus for now on cases where A is unimodular. So a matrix is unimodular. Every invertible maximal square submatrix has determinant plus or minus 1. This is really nice in terms of the theory, but also widely applicable. Lots of network tomography problems end up giving you a unimodular A. And for example, all two-dimensional contingency tables, A is unimodular. So if A is unimodular, then the union of those lattice bases is a Markov basis. And that's great because it means I can use the lattice bases as local moves in a dynamic Markov basis sampler. How does it work? I've now got a Markov process that's defined not just in terms of my vector of interest x, but also this partition pi. I'm going to update both the partition and x at each step. Now, there's a danger of upsetting the balance equations if I let the updating for pi depend upon x, so I'll just let pi depend upon the previous partition, but not x. Connectedness of the walk is assured so long as all the pi's have non-zero probability. So a very naive approach would be, you're doing your walk, you're at some particular x, you choose a new partition on the set of all possible partitions that give you an invertible A1, you calculate the corresponding lattice basis, and those are the moves available to you. The trouble with that is that calculating a new lattice basis each time involves inversion of A1. You don't have to do matrix inversion every step of your algorithm. So it'll be very slow doing that. What's more, if you do that, we're still not taking account of the polytope geometry. The first issue is actually easy to deal with. What we're going to do is, rather than updating the full partition at each step, I'll simply update it by changing one column. So I'm going to swap a column that's currently in A1 with a column that's currently in A2, or at least I'm going to propose that swap. Not necessarily accept it, I'm going to propose that as a swap. And fortunately, that update where I just swap a couple of columns is incredibly quick to compute. It turns out the new lattice basis can be computed very, very quickly, courtesy of the Sherman-Morrison formula. I have to embarrassingly admit that I've never heard of the Sherman-Morrison formula prior to working in this area. was delighted to find it in the Annals of Mathematical Statistics in 1951. Frequently, old ideas are very useful. So anyway, this means I can do column updating quickly. So the other issue is I want to be able to focus my attention, if possible, on lattice bases that are geometrically favorable. So those are ones that are going to allow me to walk around my polytope quickly. So going back to the contingency table example, let's now have the constraints as shown here, 11, 10 and 1, 10, 10. And we'll use the two lattice bases that we saw earlier, so red moves and blue moves. So these are sort of lattice bases corresponds to ones that I could pick, during my, my dynamic Markov basis sampling. Now, if I use the red basis, then it's quite clear that traveling through this polytope is going to be a very slow business. I've got a staircase up and down. On the other hand, if I use the blue moves corresponding to a different lattice basis, I can zoom around the polytope. It's quite clear that the choice of lattice basis is going to affect the mixing rate of the sampler. That's great. I now know that there are some lattice bases that allow me to, will mix quickly, and some that are less good. How do I find the good ones? If I can't find the good ones, it's useless. It's almost embarrassingly easy to find goods. You see, for any particular proposed move, you can work out the range of possible step sizes. So remember, we were taking a move view of kind of unit size and then considering a multiple b of it. But it turns out the range of b's, so the total range of movement, you can work out very straightforwardly. Unfortunately, this range depends upon the x's. And I can't let the choice of partition depend upon the x's because that destroys the detailed balance. But instead, what I can do is I can say, okay, well, let's at least focus on the x's for which the mean values of these things would be large. Not the x's themselves, but on mean values. So I'm going to want to choose partitions where I'm allowed to move quite freely. And for those of you who have been following what goes on, this is just a case of choosing moves that actually correspond to lots of slack in the linear inequality a2 x2 is less than y. As I said, I can't choose moves that depend upon the size of the x's, so instead I'm going to choose moves that depend upon the mean of the x's, or something similar, something I sort of calculate as the x's themselves. And what I'm going to do is I'm now going to choose a fitness for the columns of A. So this is what phi is. It's going to be a fitness vector. What it does is it goes to each column of A, and it basically says, okay, how large are your entries? We want the entries of A1 to be large. If the entries of A1 are large, that corresponds to a sort of slack in that linear system I've just discussed. It corresponds to zooming around the Y fibre. So something with large fitness here is something with typically large values, is typically something I want in the partition A1. And so you think, okay, I'll put the fittest columns in A1, subject to requiring that A1 is invertible. The reason, however, why I'm letting phi, this fitness vector, be random, I'm going to draw it from a normal distribution, is if I just chose the fittest vectors, I would only use one lattice basis. But I've got to be able to use all lattice bases. So according to this fitness definition, there's a chance, a non-zero probability, that any set of, any partition of A, A1 and A2, might correspond to the highest fitness. The alpha here is going to control the randomness, the noise that I'm including. If alpha is small, I have a very strong preference for only the fittest columns of A going into A1. In fact, if I set alpha equals 0, I only get the best basis in terms of the lattice basis with, as I said, the corresponding to the largest, the longest moves possible on average. If I chose alpha equals infinity, then there'd be no preference in the partition. I'd just be selecting partitions of A at random, so I'd be selecting lattice bases at random. So I'm going to work the algorithm again. I don't want to update the partitions, so how to calculate them de novo. I'm just going to think about swapping them to single columns. So what I do is I select a column that's currently in A1, a column that's currently in A2, such that a swap between those two columns is possible while A1 remains invertible. I'm going to swap them if the fitness of the vector that's currently in A2 is higher than the fitness of the vector that's currently in A1. Examples. So this is a two-way contingency table on something called the book crossing data. So the rows correspond to books identified by ISBN, and the columns to different countries. So it's a 30 by 15 contingency table, and I want to resample this. And I'm going to try 4 different samplers. A dynamic lattice basis sampler with alpha equals 0. So remember, that's where you only choose the fittest columns to go in A1. It's not dynamic, it's just a single lattice basis. Dynamic lattice basis sampler with alpha equals 0.5. It's got a preference towards the fittest columns, but we'll select less fit ones as well. And a lattice basis, dynamic lattice basis sampler with alpha equals 100 completely ignores the geometry. I'm just choosing these local lattice bases completely at random. And I'll also look at a full Markov basis, in this case with over 45,000. Here's a measure of relative efficiency. I think the trace plots tell a nicer story. So to start with, here is sampling with a full Markov basis in the bottom trace plot. This, by the way, is just for a randomly, and arbitrarily, I should say, selected entry of my contingency table, entry M45. It's the same for all of them, really. They all look like this. Obviously, the mixing is dreadful. You know, I've got here 100,000 iterations, and the effective sample size is about 3. Obviously dreadful. What about the dynamic lattice basis with alpha equals 100? This is interesting. You get long periods where you don't really get any updating happening at all. And that's because you'll have chosen some geometrically awful lattice basis. But occasionally, you stumble on some really nice one. So here, right in the middle of the trace plot, we suddenly found some nice lattice basis. And we use it for a while. Then, unfortunately, we swap to some geometrically hopeless one, and everything goes pear-shaped again. Dynamic lattice basis bases with alpha equals 0 looks the best. It's working pretty nicely. With alpha equals 0.5, it's working almost as nicely. Now, based upon that example, you may say, you've got this entire talk, and all you've done now is show us that just choosing a single lattice basis is going to work very well in practice. Hold your horses. Second example, network tomography. This network here represents a section of the A6 trunk road in the UK city of Leicester. There are 7 links, 28 paths, and I've got some traffic counts. And I've got a model with quite a good prior on lambda, which is the parameter of my underlying model for the path flows. And I initialized, as one typically does, the MCMC sampler for this problem using integer programming, which finds me a vertex of my polytope. And here are the trace plots. First, we see using the dynamic lattice basis sampler with alpha equals 0, I'm stuck. Okay, there is no updating. So here's a case where what looks like the best lattice basis geometrically, you know, sort of when on average, if you like, or sort of as a whole, actually doesn't work. It doesn't get you out of vertices. It won't reach vertices. So the random walk is not connected using this lattice basis. If you're wondering about the .g and .mh, this is Gibbs sampling and Metropolis Hastings implementation. At the bottom, we've got the full Markov bases. I must admit, I'm quite proud of this slide. because I said, full Markov basis is a state-of-the-art way of doing it. And again, it mixes so wonderfully awfully. It's just beautiful. I say again, 100,000 iterations, an effective sample size of 3. On the other hand, the dynamic lattice basis with alpha equals 0.5, that works particularly nicely here. Excellent sampling happening. Now, I did say earlier that the theory which supports what I've done works for unimodular configuration matrices, unimodular matrices A. Actually, you can extend what I'm doing to general A. The earlier theorem doesn't quite hold, and so we need to introduce some occasional additional moves based upon integer-weighted combinations of lattice basis vectors. But the sample performance remains excellent. Still some questions left. Firstly, as I said, there was a tuning parameter in that MCMC algorithm, I think alpha, which says how willing am I to accept non-optimal, if you like, or non-fittest lattice bases in order to allow me to connect my polytope. Another problem, which is really interesting, is what's the theory of the mixing properties? So it's kind of obvious that choosing these good lattice bases is working nicely, but we really must have some theory on mixing rates to support it, rather than just the numerical results. Anyway, thanks to a bunch of collaborators, Alan Lee, Bruce Van Brunt, Ginny Wilcock, Matt Schofield, Mike McVie, Rena Parry, and Timothy Bilton. Thank you also to the Marsden Fund from Royal Society of New Zealand for funding. And if you want to learn more, there's a journal article now online, and there's also an R package to implement this technique available via GitHub. Thank you very much.
Thank you, Martin. That was really good, really interesting talk and research. So does anyone have any questions for Martin or comments? Martin, I actually have maybe one or two questions. The first one is you were motivating the use of the sampling because you were saying that if you were looking at the likelihood function, you would need to basically do the sum over all the possibilities.
Yep.
That's correct?
Yep, absolutely.
So what I'm wondering is that if you want to do that to get to evaluate the likelihood, would you want to evaluate some model? And if so, would you be able to, because if you only have the marginal information, what can you say about the dependence that you would have, for example?
So as I said, typically for these problems, you will have some auxiliary data or some prior information available. So if you take, for example, the network tomography problem, yes, all that the fibre does is gives you sets of x's that are consistent with the y's. So they kind of tell you what you've learned from your data. But still, for example, yes, quite right, the likelihood will be flat in various dimensions. But then if you're a Bayesian with an informative prior, then that prior does the work of actually giving you identifiability in those directions.
Mm-hmm. Okay. And another thing that I was thinking about is, so this is for count data.
Yep.
But can it be extended to more kind of like somehow complex stuff? I'm just thinking because the count and the contingency table is, or what you have with the margin is just, a summary of the information.
Yep.
So could this be done? And I guess then the polytopes would be probably awful, but on some other summaries.
Oh yeah, I mean, sure. So as I said, the biosecurity example is really just a big contingency table where you observe things that aren't marginal totals. So some of them will be marginal totals, but you get some other strange subtotals as well. So you lack some marginal totals, you get some other strange subtotals depending upon which items have been involved in which part of the survey scheme. So certainly there's no restriction on what particular summaries you're looking at. I should also say that whilst I focused exclusively on cases where A is a binary matrix, so it contains entries 0 and 1, in principle you can extend this fairly easily to situations where A is an integer matrix.
Okay. And yeah, it's quite interesting. I'm just thinking because in some research that I've done, we're looking at aggregating some data into some summary statistics, whatever you want them to be. And then the way that then we want to get the likelihood function for these summary statistics. You have to do, and it's the same kind of stuff, the integral over all possible data that would give you this summary statistic. So, yeah, I think there is a nice relationship there.
Yeah, so I mean, people have also, of course, looked at this kind of stuff in the continuum. For example, for network tomography, there's a nice paper by a guy called Eroldi, I think it's from Harvard, in JASA, I think 2013. And so, yes, he was in the continuum. So his sampling of the polytope, which is, corresponds to your disaggregate data, was using basically a kind of hit and run algorithm where you choose a sampling direction and then sample a continuous length in that set.
Yeah, that must be a lot more complex, I guess.
No, it's actually easier. The reason why it's easier, what makes this hard, is having to remain on the lattice points. So there's no issues with connectivity there. If you've got a convex polytope, then it's fine just to choose a direction and travel in that direction. You can always reach any point. The issue here is that if you've got to keep to those lattice points, then you may have inaccessible points.
Yeah, so there's the constraints that you have to make it harder. Yeah, that makes sense. I don't know if there are any comments or questions on Martin. And Ganesh was one, so Ganesh, you can unmute yourself. Yeah, we can't hear you. I don't know if you have unmuted yourself. You raised your hand. He's lowered his hand.
Okay. Anyway, hello, Ganesh. I don't know if you know, but Ganesh is a former colleague of mine when I worked at NASA. So.
Oh, okay. Maybe it was just to, say hi. It was waving the hand.
Hi, Ganesh.
Okay, well, we can give it a stop here, I guess. If Tom is raising his hand as well, so it must be a hi.
Yes. Oh, I thought I would have to. Just keep in mind that it's like about 6:30 a.m. and I haven't slept yet, so I think I followed everything as much as I could, because it seems like everyone's doing Bayesian analysis apart from me. so let's just, if I understood correctly, so if you use the entire Markov basis, the full Markov basis, then that's equivalent to having a large value for your exploration. Did I say that right? When you're choosing the parameter to the alpha parameter.
No. So the
that's not the same, because that's what it seems to imply.
No. So a full Markov basis contains a lot of moves. So imagine you've got a long, thin. I don't know if it's going to see me drawing pictures in the air. Except this is in many dimensions. The lattice, so a Markov basis will contain lots of moves, and many of those moves will be in silly direction. So, if you've got a long, thin point like this, you don't want to be walking perpendicular to it, but move very far. You want to spend lots of time zooming up and down. So, typically, I'll give some examples of full Markov bases with, 40,000 entries. Most of those will be useless. So that's why in some of those plots I showed you earlier, the mixing was so rotten. Most of the moves in the Markov basis are just completely hopeless. So what I'm doing is that I've got a bunch of lattice bases, and by, say, assigning these fitnesses to different lattice bases, I am able to privilege lattice bases corresponding to moves that are in alignment with the overall polytope geometry.
Okay, so but it appears to me that, or at least given the examples that you've given, that like a choice for alpha should not be 0 always. So it seems like, well, given the counterexample that you gave, but I also think, well, it's my conjecture that it shouldn't be too large. So it almost always, well, my conjecture is that it should be a small value, but non-zero.
Yeah. So, and in fact, what would be really nice, in fact, just look at adaptive choices. You see, when you start off the sampler, you might be somewhere in the tail of the distribution, or in particular, right at the edge of the polytope. So geometrically, that's where it's hard. If you're against an edge, if you're at a facet or a vertex, you can kind of get trapped there. The lots of moves are impossible. And so when you're at a point like that, you probably want to try out lots of different lattice bases to find a direction for sampling that allows you to escape. So to start with, you might actually want a relatively large value of alpha, but then when you're into the body of the distribution, you probably want a much smaller one. So for the vast majority of the time, a small but non-zero value is right. If you've got a fixed value, you need something which kind of is a compromise between the two situations. But so I am pondering the possibility of an adaptive method, rather like adaptive MCMC in the continuum, where you let the value of alpha change with time. Good question. You're obviously very well supervised for your PhD. Giving you huge intellectual curiosity.
He's learned from the best.
That was a long time ago. I don't want to point it at you, but that was also a very long time ago already.
It was a long time ago now, I have to admit, yeah.
All right. Yeah, I guess we can maybe call it off now. I'll stop.